Okay, so we have the formula for the Taylor polynomial. It's basically building on the linearization. So if you want the nth order Taylor polynomial, then that means the polynomial of at most degree n. That's a good approximation to this function in the sense that it matches all the derivatives of the function at the center point up to n. So see, there's the first part of the Taylor polynomial is the linearization. That much is p1. You keep adding in terms. You add a quadratic term, and then you add a cubic term, and a quartic term, and a quintic term, and so on. You can add as many terms as you like, so you could go all the way up to the nth degree. Okay, so if we look at this formula, if you want to find the nth degree polynomial, you need the function and you need its n derivatives. You're going to have to calculate. You need to have that center point, x naught, so that you can evaluate the derivative at that point and plug that point in here. And you're also going to have to calculate these factorials. But you remember what factorials are, right? N factorial just means n times n minus 1 times n minus 2, and so on, until you get down to 1, and then you stop. For example, 2 factorial is 2 times 1, that's just 2, and 3 factorial is 3 times 2 times 1, that's 6, and 4 factorial is 4 times 3 times 2 times 1. That's basically 4 times 3 factorial, right, which is 24. So that's where the numbers here in the denominators are coming from. And they're just there so that when you start taking derivatives of the Taylor polynomial, then by the time, say, you've taken 5 derivatives, you would have had a 5 come down, and then a 4, and then a 3, and then a 2, and then a 1, and that would wipe out that coefficient, and you'd be left with just the 5th derivative of the original function. So those are there to make the derivatives match up. Let's do an example with this function here, sine x. So first, we know since we want to do the 5th order Taylor polynomial that we're going to have to find 5 derivatives. So let's just calculate the derivatives. The derivative of the sine is the cosine. The derivative, so the second derivative, take the derivative of that, right? The derivative of the cosine is the negative sine. The third derivative of the sine is the cosine, so we get negative cosine here. The fourth derivative, when we start to write too many primes, remember we can just put the number of derivatives in parentheses there, so that means 4 derivatives of f. Well, the derivative of cosine is the negative sine, but there's another negative here, so we're back to sine. And then the fifth derivative is going to be back to cosine. Now at our particular point, we're going to do this at 0, so that means x naught in this formula is 0. Sometimes this formula is written, instead of using x naught, they write a, so you'd have a here and a and a, but you can convert the formula if you see it some other way. You know that it's just talking about a or x naught. It's the center point for the Taylor formula. So if the center point is 0, sometimes we call that a Maclaurin series or a Maclaurin polynomial. We'll just call it a Taylor polynomial. Let's see. F prime at 0, that would be the cosine of 0, which is 1. F double prime at 0 would be negative sine 0, which is 0. F triple prime, the third derivative at 0, would be negative cosine of 0, which is negative 1. The fourth derivative at 0 is, let's see, the sine of 0 again is 0. And, oh, I forgot to do f at 0, which is 0, isn't it? And the fifth derivative at 0 is the cosine of 0. That's 1. So if we put this together to find p5 for our function, we're going to have the function at the center point, right? F at x naught, we figured out, is 0. And the first derivative is 1, so we get plus x minus 0. And then the second derivative was 0, so this term doesn't even show up, right? And then the third derivative was negative 1, so we get negative 1 times 1/6, right, from the formula. 1/6 times negative 1 would be negative 1/6. X minus 0 cubed. X minus 0 is just x, right? The fourth derivative is 0, so this term doesn't even show up because that 0 wipes out that quartic term in the Taylor polynomial. So we go up to here, we've got 120, the fifth derivative is 1, so we got 1 over 120 times x to the fifth. So 1 over 120 times x to the fifth. Now that we've got that Taylor polynomial, let's compare it to the original function. So here I have the graph of sine of x. That's the function we're trying to approximate. Remember, we've centered this at 0. So looking at that, our first Taylor polynomial was y equals x. That's a good approximation until you get closer to pi halves, where sine starts to roll over here, right? So sine starts to roll over, and that's where they start to diverge. So we saw that in our polynomial. Then we added in this x cubed term, so x cubed over 6. See how that gave it some curviness there. Then we could add in our next term, which was x to the 5th over 120. We get better and better. Now you may have noticed that there was a pattern here in the derivatives. First off, every other derivative was 0, so you never got any even terms in the polynomial. And then the ones that were non-zero alternated between negative and positive. So we can guess the next term coming up is going to be x to the 7th, but it's going to be over 7 factorial. Let's see. So that is, what is 7 factorial? Well, I'll just do 7 times 6 times 120, since I know 5 factorial is 120. Okay, see how we got an even better approximation. And we can keep adding those in. Because of the pattern, we saw that this was going to be 9 factorial. So 9 times 8 times 7, and is x to the 9th term. And this one was going to be positive. It goes further and further. So sine is an example of a function that whose Taylor polynomials, they just get better and better. We would say there's an infinite radius of convergence. You can just keep adding more and more terms to the Taylor polynomial, and you can push this out further and further and further. And you see this final one, this 9th degree one, is already pretty good, almost all the way out to negative pi and pi. Also, an interesting thing about this is if you have an odd function, and sine is an odd function, then it's only going to have the odd polynomial terms. The rest, the even ones, will be 0.